Maybe shall we start?
Yeah,
Okay, I'll introduce and then we can start.
sure.
Good evening, everyone. Welcome to Network Seminar Series hosted by the Center for Networked Intelligence at the ECE and RBCC. It's my pleasure to introduce today's speaker, Professor Saurabh Jain. He will be speaking on multi-paradigm simulation for decision support case studies in public health and healthcare systems. Dr. Saurabh Jain is a faculty member in the Department of Industrial Engineering and Operations Research at IIT Bombay. He received his PhD in Systems and Industrial Engineering from the University of Arizona in 2021, where he also earned his MS and uh, MS in Industrial Engineering in 2017. Before joining IIT Bombay, Dr. Jain worked as an operation research engineer at Intel Corporation USA, where he designed and developed high fidelity simulation models to evaluate fab performance under varying production, layout, and WIP management strategies. His research focuses on applied simulation modeling and analysis for large scale systems, with applications spanning manufacturing systems, healthcare systems, public policy, border security, and social networks. Dr. Jain has authored and co-authored several publications in international journals and conferences of repute. He is a member of the Institute for Operation Research and the Management Sciences, the Institute of Industrial and Systems Engineer, and the Society for Modeling and Simulation International, Society for Simulation and Healthcare, SSH. We request the audience to keep your microphone silent for the duration of the talk, except while asking questions. Questions can be asked at any time during the talk, either by unmuting and speaking directly or by typing them in the chat box. Over to you, Professor Jain.
Yes. Thank you, Strashma, for the nice introduction. Good evening, all. And first of all, happy Diwali to everyone. So I'm here to present some of my past works in terms of like on the topic multi-paradigm simulation for decision support in several applications in healthcare systems. So and just to give you a brief overview of my current, just to introduce myself, whereas Sushma already did a job. So I am basically a mechanical engineer by training in BTech, and then I pursued my master's and PhD from industrial engineering from University of Arizona. Uh, Post my PhD, I earned 3 year experience as operation research engineer at Intel Corporation, Chandler, USA, and subsequent to that, I joined IIT Bombay last year, where I'm serving as an assistant professor in the Department of Industrial Engineering and Operations Research. So my main research lies at the intersection of simulation modeling, AI, and different types of these decision support methodologies. Uh, on from the computing side as well as from the hardware side as well. So I work a lot with integrating a lot of sensors, robotics, and different types of VR, AR kind of headset, and all those type of technologies in order to support decision making in different types of application areas. So here are some of the snippets that I recently I work very closely with the domain experts. As you can see, like when working with like these healthcare settings, I always try to engage as much as possible with myself in order to observe the system so that I can model it at the greatest level of detail. So as I already mentioned, in terms of research interest, I'm currently heading a smart XR lab, which I'm setting up at IOR IIT Bombay. The focus of my work and some of my students, we are working on at the intersection of multi-paradigm simulation modeling, where we have all sorts of like tools and techniques that we can use, like discrete event simulation, agent-based modeling, and physics-based modeling, along with the evolving artificial intelligence and how these technologies can be integrated together for serving different types of purposes, be it a human in the loop type of system, hardware in the loop type of system, or a standalone decision support system, which can provide the decision makers and different stakeholders with insights on any kind of problem. So I work predominantly in healthcare field where we have currently two different types of projects that are already ongoing, but I'm very much interested in exploring manufacturing as well as some of these smart city and networks type of applications where we can integrate collect real-time data from for a environment or for a like surveillance type of environment, which can be integrated into some of these decision support tools to provide the real-time insights to the decision makers regarding the strategy, be it insights or anything like that. So here I'm going to talk about some of my previous work. So just to start with modeling. So of course, we all are must be familiar with what modeling is. So when we cannot do certain type of like experimentation and testing out our different types of strategies on the actual system, then we resort to modeling. Modeling can also be broadly classified into two different types of methods, which are analytical modeling, which is mostly developing high fidelity mathematical models, and the other part is simulation modeling. Now, in terms of simulation modeling allows us to perform different types of what if analysis, and it helps us in achieving some sort of approximate solutions to any real world problem that we are modeling. Now, modeling, there are different types of modeling paradigms, right? For example, we have discrete event simulation, we have agent-based modeling, we have system dynamics, and we have some evolving paradigms like physics-based simulation, which definitely has to be chosen based on the level of abstraction we want to integrate into the sort of system, right? So to start with, one is like discrete event modeling, where we are basically dealing with some sort of like passive objects which have sort of defined route within a system. For example, if we talk about manufacturing shop floor, there the passive objects, the entities can be considered as a part that need to be manufactured machined, and there are like several other machining processes that need to be integrated in together on that production line, and based on that the part has to follow that particular route or set of rules to get through the system so that we can get the desired or the evaluation metrics that we are basically looking for. The second part is more of agent-based modeling, where it is slightly more decentralized, where the focus here is how the different active entities within the system interact with the environment as well as the other agents. So now in this type of agentic behavior, we are more interested in observing how the system is basically evolving over time, and based on the horizon that we are trying to observe, we try to get insights on how system has evolved over time by agents performing different types of interaction with the environment as well as the other agents. And it has also been much more of an evolving paradigm, because nowadays with this artificial intelligence being incorporated into different types of hardware systems like robots or other types of things, it's also in order to integrate these kind of system to basically simulation, this ABS is more of a preferred type of methodology. Uh, and it basically operates based on the state charts, which basically defines the set of states that agent is going to observe throughout its time, based on the interaction, based on the system state change, based on a simple timeout or something like that, right? Now, third part is like system dynamic, which is more of an abstract type of modeling, where we are dealing with sort of stock and flows, which are basically governed by a set of differential equations. So one most common example is if we are trying to test out how an innovation in the innovation, or like let's say a new product in the market comes out, how does it evolve in the market, how does it get adopted into the market. So all those type of dynamics can be efficiently captured by system dynamic type of modeling. So now, since I already mentioned that predominantly my work mainly focuses on healthcare type of applications. So in healthcare type of applications, we are mainly dealing with four different types of or four different kind of classes of problem that we are working with. So one is with predictive analysis. So nowadays, with evolution of a lot of AI ML type of modeling, there is a huge scope of being utilized in like diagnosis. For example, utilizing MRI scan, CT scan, all of this data can be fed into AI ML models, which can provide us with some sort of insights regarding the how disease is going to propagate and helping us in taking an reactive or proactive action on time. The second aspect is simulation modeling, which is still a most set of traditional type of OR problems in healthcare, which is like resource allocation, how we can allocate a resource allocation in a healthcare setting or an hospital or any kind of healthcare provider center. The third one is sort of a decision support systems, which are mainly dealing with providing sort of personalized treatment recommendations for one case or the other. Or one of the aspect of real-time decision support system is providing for patient X versus patient Y, how we can provide a personalized sort of training or insights on their thing, right? And the fourth aspect that I predominantly work with is VR AR in sort of a medical application, where VR AR with a high fidelity like visual displays and 3D environment, how we can leverage this technological advancement with the VR AR devices, for example, HTC Vive, Samsung, Meta, and all of these companies are producing more and more VR, AR type of devices. How we can leverage this technology, how we can leverage these devices, and in-house, how we can develop some sort of decision support models, or how we can develop simulation, high fidelity simulation models, which can be used for training and surgical planning and navigation type of applications. So this has been one of the key area of my interest as well, where I try to integrate different tools and different techniques for uh, performing different things. So I'm just going to jump into the first use case that I'm going to discuss as a part of this talk, where we are focusing on how we can develop an VR-based simulation for minimally invasive procedures. So the challenge with minimally invasive procedure is, so first of all, with minimally invasive procedure, the thing is the surgeon has to involve into a high amount of hand-eye coordination, because he has to operate into the operating field, utilize by looking at a two-dimensional screen and camera tool in one hand and the surgical tool in the other hand. So it requires a sort of a bimanual dexterity, and there's a steep sort of a learning curve that uh, that that is observed while performing the training. And also there is some challenges associated when it comes to intraoperative procedure. So our goal is to how we can actually make this training aspect easier, as well as how we can aid the surgeons while performing the surgical processes intraoperatively as well, by integrating some of these sensors that we can borrow from this VR, AR, and technological advancement. So as I already emphasized, first of all, it is a two-dimensional screen. So that's why it has a monocular visual display, which lacks sort of a depth perception. The second aspect is, since the camera tool, and because we are not making a sort of a cut or anything in the patient, so that's why it requires, the tools are predominantly long, and there is a huge amount of training that is required in order to get feel of actual tactile feedback and all the hand movements that they are performing, because it sort of get amplified when you are trying to operate in that whole space. So the concept is, of course, very simple. So our goal was to provide a high fidelity training environment utilizing this virtual reality technology for basically some sort of residency programs. And it was actually, our tool was actually inducted into one of the residency programs at University of Arizona. So it comes with the combination of like physical reality and the virtual reality. So this virtual reality technology, if we wear goggles, we see a nice 3D space and nice visualization, and we can perform the multiple trials on a patient, as well as it is reusable, and all those type of things is basically provided, and it provides an enhanced sort of cognitive feedback to the user. Whereas the other aspect is the tactile feedback or the haptic feedback that is actually missing from these VR, AR type of medical trainers. So our goal was to bridge this particular gap. So our goal was to provide a cognitive, high sense of cognitive feedback via aided simulation cues, via adaptive step-by-step guidance, and all those type of things. The other aspect was how we can integrate the very realistic haptic feedback into the system so that the practicing surgeon or the operating surgeon actually get a sense of handling the real world procedural tools in that aspect. So it actually is a combination of physical reality and a virtual reality. I'm going to explain in a little bit. The other aspect is, now when you are trying to combine a physical reality and the virtual reality, it comes with its own set of challenges, which is of course the calibration, right? So you are, in a way, you are trying to superimpose the virtual objects that you want to provide to the user onto the physical physical environment, right? So it requires the calibration from both aspects, which is positional aspect as well as from the parametric aspect. So in terms of modeling, we actually utilize the real world data from some of the de-identified patients, which was like CT scan data. And based on those CT scan data, we performed some sort of reverse engineering where we try to obtain the geometry or the mesh related to the anatomical structures that are relevant to this particular uh, surgical aspects. The second aspect that we did was we try to integrate the tools that are relevant to these surgical uh, this particular surgery as it is. So we modeled those surgical tools based on the specifications provided by the vendor and everyone, and how we can basically model those tools and bring it into our VR environment so that surgeon can actually get the feel of uh, performing the surgery using the real tools and on the real CT scan and real anatomical structures for a particular patient. Now, this basically serves purpose in multiple ways. So one thing is, this particular system, first of all, it allows you to perform sort of pre-operative planning to the pre-operative planning to the doctor, because when usually in practice, when doctors are going in for the surgery, they traditionally look at a two-dimensional CD scan and then get an idea. But however, in this kind of system, if you can plug in the CT scan of the patient that you are going to operate on in a few hours, that would actually provide them with much more enhanced method of planning. The second aspect is it will be a good way for users for and also for medical companies who actually supply these surgical tools to test basically. So this will actually provide these companies with some sort of headroom in order to uh, use these surgical tools, test out their newly upcoming tools into the system beforehand, and get some feedback from the uh, from actual doctors who are going to use it. So now once we have all of these aspects, like once we have incorporated the real CT scan data, once we have incorporated the surgical tools, now it's part of an implementation. So we modeled all of the operating room environment into the Unity 3D, which is widely known game engine, which is used for developing some virtual reality simulations. And in Unity 3D, we also made sure that we can provide some virtual environment to the user, which resembles to the actual operating room, so that he can actually get a feel for how operating room looks like, and we can incorporate as much as realism to it. For example, the sounds and the beeping and all those type of, and some extra screens that are provided for the navigation of the doctors and so on. So it basically helps in enhancing the realism and actually provides a very concrete cognitive feedback to the trainee in order to perfect this kind of surgery. So we utilized full room scale virtual reality setup, which is called as HTC Vive. So HTC Vive is nothing but it provides a VR setup which can be scaled to a like room, 6 by 6 room for an accurate tracking. And in that 6 by 6 room, the user can actually walk within the virtual reality environment, and he can perform different types of tasks based on what has been modeled into the uh, uh, VR. So as I already mentioned, we incorporated all of the relevant anatomical structures based on the real CT and MRI scan. This actually included some sort of segmentation using some pixel-based intensity. And based on the segmentation, we performed some mesh reconstruction for those relevant anatomical structure, because we don't want to bring in the unnecessary structures which are relevant. We just try to tap that particular part in. The procedural tools, of course, will require a lot of CAD designing in terms of how the tool looks like and how we can incorporate the tool with the appropriate dimension and scale that has to be taken care of. The third aspect was patient specific, 3D interactive patient specific module, which basically includes all sorts of operating room environment, which had all sorts of surgical equipment, machines uh, that are required at the time of surgery, and uh, like different types of uh, layout that has been incorporated as per the real operating room. So, the glimpse of it is shown here. This was our developed operating room where we had a set of surgical tools, the patient, and we had a real-time video of the. We had the video feed also for the operating field to provide some sort of guidance to the user. So once we have developed this type of system, it is good for training. I agree, and we have a lot of potential in order to how this particular system can be utilized into the future. So one aspect of it that we try to explore was we try to provide some sort of framework that can actually perform the objective proficiency assessment. So right now, what happens in these type of traditional setting is we have a surgical training programs where there is an instructor already uh, uh, instructor taking on to the trainees and performing like different types of procedure, different steps of the procedure, and most of those feedback or assessment is sort of subjective. So there is, like, for example, I have attached a template on the top right corner where the instructor has to sort of fill out a form uh, based on the performance of the trainee. But how can we make this whole exercise of performing the proficiency assessment objective? So now, with advent of this whole AR VR devices which are being tracked in the real time, we get to choose how we can actually perform. We get to actually choose to how what data to collect, what is the optimal level of data that we can collect, optimal frequency of level of data that we can collect. We have all those knobs that can help us basically adjust uh, the fidelity and the resolution of data that we are sort of collecting. So we wanted to leverage that particular aspect of it, and we want to integrate it with sort of some small AI type of system which can actually read all of that real-time data and provide some sort of feedback to the user. So this particular part of the presentation will focus on how we actually got all those type of data, and we can provide some sort of objective feedback to the user. So in terms of data collection, of course, the static data collection in terms of the completion time, in terms of the number of consultation that user is taking while doing the performance, and also the number of hits to the critical structure. So there are a lot of in this anatomical structure, there are a lot of aspects where the user or the trainee doctor should not be hovering his tool kind of thing. So I call them sort of no-fly zones where the user's tool should not be present because it might lead to some damages to the patient. So in order to account for all those type of aspects also, we took into account this number of hits to the critical structure, because definitely naturally the novice users are tend to do that. Now, in terms of dynamic data collection, we used a lot of this tool motion data, of course, which are being used in order to perform any kind of dissection. And the second part is the endoscope motion data, which is nothing but a camera tool that is displaying what surgeon is actually seeing on the screen. Uh, so we essentially try to uh, track the motion and track the uh, tooltip of these tools basically in over time of simulation when we perform, and based on that we try to use all of that data in order to perform the objective assessment. In order to perform and collect a lot of these data, in order to conduct all of these validation studies, I actually personally myself attended a lot of ENT conferences because this procedure is related to ENT. So I attended a lot of ENT conferences across the US um, to collect considerable amount of data with varying level of proficiency levels. So we were able to collect around 48 subjects data worth of data, where we divided them into basically two groups based on the number of years of experience. So the first group was labeled as sort of a novice, and the second was labeled as sort of expert. And of course, like as I already mentioned, we can also control the set of resolution of the data that you want to collect. So we had a frequency of 10 data points per second, which was quite high. And it basically, we just wanted to get to the lowest level of granularity. That was our focus. Now, when we are doing this kind of like data collection, it is also important we do it in a sort of a structural way. Now, because in VR environment, one person put on goggles, there is a lot of chance, and there is a high chance that people will perform some random motions and all types of activities they will try to do, and try just in order to get comfortable with that whole virtual environment. So in order to make that part structured, we try to divide some initial part of that particular surgical procedures into 4 steps, which are namely step 1, step 2, and step 3, step 4. And once the user tries to initiate step 1, then there is no going back. He will have to perform all 4 steps, because they are sort of aligned and just one by one. So basically, we made sure that we utilize some framework called as hierarchical task analysis in order to structure the surgical tasks. So here, the whole procedure that served our purpose of our interest was maxillary antrostomy, which is one of the procedure for this endoscopic surgery, where we divided it into one level of granularity, where we first part was enter the nasal cavity, perform the lateralization, medialization, and then the final step, that is the last one, which is uh, the actual maxillary antrostomy. Now, this is at the higher level, right? So this will actually provide me with the data associated with completion time, hits to the critical structure in the while performing this task. But when I'm collecting the motion data, now it is very important in actually uh, in order to perform how different steps were performed. So basically, we had to get down to one more level, which was more focused on the tasks like picking up the endoscope, and then surgical tools, entering the operative zone, actually, the nasal cavity, and optimizing the camera position, because it is all about getting the right view while performing the procedure. And yeah, so we just actually performed all of these steps, and some of the brief idea on what time was taken for each of these steps are mentioned on the right side in seconds. So this was like not too big of a task was taken into consideration yet for this particular study, because we wanted to limit the boundaries, and we did not want to have too much of an noise into our data set. So once this all data set has been collected, the first important part was how we can actually pre-process this data. That is the important aspect. So we had around 14 fields in terms of the real-time dynamic data that we were collecting, which was nothing but the XYZ coordinates of the endoscope, XYZ coordinates of the tool and rotation, and all those aspects. Now, when it comes to any kind of surgical proficiency assessment, and we are trying to perform some sort of classification in terms of whether the current trainee is an novice or an expert, right? We need to make sure we need to actually compare it to one reference, right? But so, for example, the uh, two trajectories shown on the right bottom corner, we need to perform some sort of, in order to like convert it to the rectangular data, we need to compare how different the current training is with the expert user. But in terms of these surgical processes or any kind of processes where human is involved, we are not sure what to label as experts, right? Because in especially in these surgical processes, it is highly possible that two expert surgeons might have totally a different set of uh, surgical styles, or the way of operating, or the way of how their like tools and trajectories are moving. So in order to make sure that we are comparing to a reasonable baseline, of course we cannot achieve to the ground truth of how the expert surgeon's trajectory will look like. We will sort of we sort of utilized dynamic time warping in order to perform this particular part of pre-processing. So with dynamic time warping, first of all, we utilized it to combine the motion trajectories of four different experts having different levels of experiences in terms of years, as well as specializations little bit different in terms of the surgical experience. So based on that, we try to mix as much as we can in terms of the expert truth, so-called expert truth that we are trying to establish. The second aspect was we try to utilize dynamic time warping in order to compare all other trainees to our established ground truth. So basically, how dynamic time warping works is it it generates this whole matrix based on one-to-one comparison between the data points in two different type of trajectories, and based on that, it develops a uh, cost thing. And based on that, we use that cost to actually implement the machine learning in order to actually perform the classification, because we wanted to combine both type of data, like static data as well as dynamic data. But dynamic data was more of a time series data. So in terms of this dynamic time warping, the ideal warping path, definitely when two trajectories are exactly identical, it has to be sort of a diagonal type of thing. But in terms of this uh, in terms of the in this particular application, it is of course not possible. So that's why we try to compare. Now, just to give you a sort of a glimpse of what different proficiency levels actually provided us with. So, for example, this was just a small demonstration in terms of the velocity of the tool movement while performing the this particular procedure. We try to these are the plots for the warping path for these three different combinations, right? For example, expert versus novice, expert versus expert, and novice versus novice. Now, in terms of similarity, as I already mentioned, in dynamic time warping, when we achieve that 45-degree line, that means the ideal path and two trajectories are almost very close to each other. So, but here in case, these results were actually insightful, where when we look at expert versus novices, there was clear differences in terms of first of all data points. The trajectory obtained by this novice was way bigger than the trajectory of an expert, which must have been pretty straightforward. And based on that, of course, there were like a lot of places where this whole warping path went flat, which basically denoted that there might be a lot of extraneous movement or sort of an idle movement that might have been performed by the novices while performing the procedure. Whereas on the contrary, if we look at expert versus expert, which is very close to the data points are also very close to the number of data points also. And also in terms of the warping path, it is seems to be reasonably stable along the 45-degree ideal path that it should have. The third case was novice to novice, which was also very reasonably similar, but there are a lot of aberrations in terms of along the warping path or ideal warping path itself, which denoted the difference in terms of styles among the novices also, because they are not that level of expert in performing this particular surgery. So this was actually clearly observed and validated when we implemented this whole dynamic time warping in order to classify the proficiency level. Now, once we classified, we utilized this simple decision tree C 5.0 in order to actually perform the proficiency classification. So now we have the similarity metrics for all the 14 features for the continuous movement, whereas we also had some of the static measures like completion time and so on. So, and we were able to actually, when performing the decision tree C 5.0, we were reasonably able to well accommodate all of these like clearly able to classify, and also we got some of the insights on what features actually led to this particular differentiation. So that was the key highlight of this. So now this actually provided us with some insights on the difference in the proficiency level of the users. So I'm just going to show some small demonstration that we developed. So I'm not sure like whether sound is audible. Uh, but here we have like these surgical tools, and so this was the 2D screen that they have to observe. And based on that, we provided the high fidelity. We also have a voiceover, which actually provides the user with some sort of guidance in terms of what is the next step. And also we can see the simulation cues are clearly visible on which which structure to focus next and all those type of things. And we also provided some sort of real uh, video as well, so that uh, people can practice by looking at one on one. So this was the first aspect of my simulation. The second was related to something called as where we did a project while the COVID hit for the pandemic modeling. So the focus here was to develop a system or decision support system where we can help the university stakeholders in order to take the um, decisions associated with like university reopening, how we on what mode we should conduct the classes, and so on. So in interest of time, I'm actually going to go over it little faster. So as we already know, in terms of pandemic, like it was hit, and there were around 110 million cases of coronavirus, more than that actually, and there was unfortunate people lost their lives as well. The main important lesson that it gave us is like it actually interrupted a lot of schooling and interrupted a mode of this delivery of education and all those type of things, and even our day to day in even our day to day activities. So as soon as this whole the COVID-19 hit, the University of Arizona. So this project is from one of my one of my projects when I was a postdoc at University of Arizona, where we had to design sort of reopening policies in terms of how we can actually perform different type of what if analysis regarding the classroom, regarding how classes should be organized, what should be the changes in the schedule. So we approached this problem and we took a look at it in two different levels. So first level was the higher level, which basically focus on campus wide sort of modeling, whereas the second aspect was on the lower level model, which was more focused on the lower level aspect of things, which was namely buildings. So basically, we try to model the aspect of, for example, each different type of classrooms, different type of buildings, dormitories. And based on those activities, we try to aggregate some of the parameters that can be useful for uh, higher level model. So at higher level model, it helped us in predicting the campus wide decisions, right? Like much more of a broader set of views. So first, I'm going to go over what this higher level model entailed. So in this, the goal of the model was, of course, to predict the disease propagation at the university level, and this helped us in performing different sort of evaluation policies for pandemic control. And the modeling paradigm that we chose for was definitely agent-based simulation, because here the focus was how, because with this whole like COVID-19 and pandemic, we did not have any idea on how actually next month is going to look like, kind of thing, right? So the best thing is what we knew was from the behavior of different students, different teachers, different faculty members and staff at the university campus, and we wanted to see how the system evolves over time, given some of the assumptions of this uh, disease propagation, disease transmission, and so on. So we were actually working closely with some of the public health collaborators who actually provided us with some insights on how viral infection is spreading, which played a vital role in basically informing some of our agent-based modeling. Right. So there were basically three different types of components that we wanted to focus in terms of high level modeling. The first aspect was, of course, mobility. So in terms of mobility, we wanted to cover how the students are going to move from dormitory to their classroom to different test centers and all those type of aspects. The second aspect was disease propagation, of course. So there was like, of course, we were doing a continuous tests, like antigen test was being performed every week or so on different like cohorts of students. Based on that, whatever we identified like of infected individuals, we were able we wanted to see how the uh, how the disease transmission will take place in next course of time, based on the whatever interaction that particular student will have with other individuals as well as with the environment. And the test and treatment is, of course, we had a lot of policies in place for testing. For example, every week a student has to go for a test kind of thing. And treatment, of course, we had some sort of dormitories that were specifically assigned for quarantine and isolation type of activities. So in terms of agent-based modeling, we modeled this whole system where we had system as a campus, university campus, and we used a simulation tool called as Analogic to model the system that is our university campus, and there were a lot of agents associated with it. So these agents were nothing but students and other stakeholders within the university. So each agent will basically, the focus was with each agent will basically assess their states, make decision based on some set of rules, and these rules were derived from the class schedules, infectious risk, and test schedules. So these were also provided to us in the form of data because we already know all the data where we know that okay, which courses the students are enrolled into, where are the classes being held, what is the class capacity, what is the what are the number of seats that are available within that classroom, and how many students are enrolled into that particular classroom. So uh, now in order to define hybrid modalities and now answer all of those type of questions, it was very important to have all these type of data in place. So, so this was all part of the mobility where we had each data associated with each individual student agent, and that has been fed on this analogic simulator where we can have some nice GIS data loaded into it, where this whole routes are available. So this was a small dashboard that we developed during that time, where we try to nicely capture all of the academic buildings that are important, and also what are the states of the students that are transmitting with small dots. You can see like a green dot basically say susceptible because they are not yet infected, and so on, right? And based on that, we try to ingest this into this simulation. We try to ingest all of the schedules of each type of agent, and based on that. So now, when it comes to this, was a part in mobility where we lay down the foundation of our university campus, lay down the foundation of like the routes that each agent has to go through, kind of thing. Now, the second component was disease propagation. So now how we will model actually this whole disease propagation. So in terms of disease propagation, we took into account two different aspects. So first aspect was droplet transmission model, which is nothing but a sort of a Gaussian plume model that we considered into account, where we are trying to like based on some interaction between two agents that are standing next to each other, how much like viral load or like the droplet that particular agent is putting into the air, kind of thing. The second aspect was related to airborne transmission model, which was also on dose response model, where if into a building, if we are talking about a building where the class is being organized, how based on the number of people present into that particular classroom, how does that affect the airborne quality and all those type of parameters, so which incorporates all sorts of ventilation conditions and all those type of things. So we incorporated that part into this airborne model so that we can provide the we can actually try to define how much viral or infection a particular agent is being exposed when he's attending or he's in a proximity of a particular sort of a building. So the other aspect was the so this was about classroom and all those type of things. But now the second aspect was the dormitory. So dormitory also there was. So at that time, of course, the university took some decisions to send people home and also reduce as to much extent they can separate people living on the sharing basis, but still there was a good amount of chance when people get infected while they are in sort of a dormitory and they're sharing a room or sharing a mess or that kind of thing. So basically, we had incorporated all those aspects in terms of dormitory disease transmission. The another aspect was related to this off-campus disease transmission. So university has everything in control in terms of if we are like modeling dormitory, if we are modeling academic buildings and all those type of things. However, whatever you do, what can you do? People living off campus. So there is a good amount of students, good amount of faculty, good amount of other people that live actually off campus in these kind of US universities. So, for example, most of the graduate students, international graduate students, they live off campus. So, how do you trace all of those aspects? So, in order to aggregate the parameters associated with that, we had the best guess, which was R naught value, which was being published by the government at that time. So we tracked that R naught value, which R naught value associated with that particular zip code around the university campus. So we used that R naught value in order to define and incorporate the, the disease transmission that might be caused due to the people living off campus. Now, there is another aspect like off campus is not only about people living off campus, it is also about some of the people going from campus to off campus to do some party or some doing some gathering, because even if you have this shelter in place kind of order and everything, it does not stop it all the time, right? So that's why we had to take into account all of those aspects, like if some students are holding some gathering off campus, having some sort of party kind of thing, how we can trace it. So that particular aspect also was incorporated into here, and these were the typical policies that we had in place at that time, which was like only essential classes, like for example, 0 to 2 classes per week for each student kind of thing. Um, the student living on campus will receive some sort of antigen test on uh, uh, very regular basis, and also party size and all those type of events were still happening, right? So we had to take into account all of these aspects, and based on that we defined our simulation. So for our simulation we did this run for around 15,600 students, with where, as I already mentioned, we had a huge chunk of student living off campus dormitories as well, which was 9,920. And we, based on that particular initial conditions, we had some set of infected students, isolated and immune students, and 90% of mask wearing was a policy at that time by the university. Like they wanted to encourage it, but it's not always possible to achieve 100% kind of thing. So we evaluated our simulation for different type of scenarios, because even though we have these policies in place, but it's not going to happen that we are going to the students are going to follow it to the fullest level, right? So that's why we try to evaluate and run our simulation for two extremes. So which was, one of them was optimistic scenario where 100% of the mask has been followed, no party or gatherings have been happening, and very shelter and at home has been followed very strictly. Whereas on the other extreme, we have the pessimistic scenario where there was a significant amount of gatherings happening. People are not staying much at home, kind of thing, uh, and and so on. So we try to run the simulation for all those type of level of scenarios, and based on that, our simulation also had around 51 buildings on campus, which was the real number, and the dormitory, and we also took into account around 1200 antigen tests per day. So based on the running the simulation at that time, we were able to predict to a reasonable level of accuracy. So I'm just going to skip this. So this was the sort of a validation that we performed at that time, where red line basically showed the real data, which was being published by the university uh, on a daily basis, basically. And subsequently, for 1 month, we also try to perform our predictions based on our simulation. And our simulation results were quite close, I would say, with some residual of 8.5 cases per day here and there, which was pretty okay in terms of what should be like what can actually help the university stakeholders to drive some of these decisions. So this was one part. Now, the where does all of this data into these disease transmission model will come from? Droplet transmission model and airborne transmission model. So here you might have seen some parameter called as D, which is nothing but particles spreading between 0 and 3 feet. Like if let's say two agents come in contact between 0 and 3 feet, and we divide it into two different types of buckets. So these were sort of we modified our Gaussian plume model. So now where does this whole data come from? So this basically all of these data came from our lower level model. So in terms of lower level model, so I'm just going to quickly go over it. So in terms of lower level model, our focus was to how we can, if we are talking about a classroom, if we are talking about a dormitory, mess, or anything, and different types of classroom, different layouts of classroom, how we can actually evaluate the entry exit policies, how we can evaluate the average contact number that each agent has gone through, average contact time or exposure duration that each agent has gone through, kind of thing. So that was the main motive of capturing the lower level model. So in this, like we utilized a lot of like social force model in order to capture this pedestrian behavior, basically. So social force model is a widely known model proposed originally by Helbing, where it is basically a combination of different types of forces that is being exerted on a pedestrian by external environment, other agent, and also the the desired velocity or force it has to complete, right? Desired velocity or so on, right? So it is basically a social force model, and we try to model our pedestrian behavior that are walking onto the classroom, onto the other parts of the building using the social force model, so that we can define the behavior between two agents much more accurately as possible. So there were definitely different types of challenges that we came across, and at that time we definitely had some policies associated with social distancing, physical distancing. So with the social force model and its modified version, we were able to incorporate how we can define the social force, the social distancing policies into place. So, for example, if we had between 3 to 6 feet contact, which is like most desired amount of distance two agents was to maintain, versus when we have this whole violation of social distancing taking place where agents come too close to each other where it is violated. So we wanted to capture all of those dynamics that are happening into the system so that we can aggregate those parameters to our best of our capabilities and feed it into our high level model, so that uh, at a university level we can get much more clearer picture on what policies would work versus what policies would not work. So so this is just a small example of one of the classroom that we designed. Um, so here you can see the students are coming in of the campus and into the classroom, and we have different set of seating policies that were available. So we actually came up with uh, proposed algorithms that can actually help us in identifying how we can place different set of uh, students, like how we should assign them the seats, how far the seat should be assigned from the doors to minimize our area, our parameters of the interest. For example, number of contact hours and number of people that are coming into contact, and exposure also to the other agents. So this was the focus, and there were a lot of challenges when it comes to defining the simulation. So, for example, we tried to model all aspects into terms of like types of classroom. So for example, you can see here we had four different types of layout basically. So these were all based on the real data for each type, and we try to group all the similar type looking classrooms and try to aggregate the information and simulation output to provide it to the next level at the higher level. So yeah, so I think that was the main part of it, and the results also were pretty much aligned with what uh, intuition we had in our mind when it comes to modeling this particular system. So, and we also try to basically test out different types of exit policies, test out different types of seating policies, and we try to see how they impacted. So, for example, here you can see we tried out on the right hand side, we tried out zonal exit versus non-zonal exit. Like in non-zonal, everyone starts to go out of the classroom versus in zonal exits, we divided this whole classroom into different zones, which actually reduces sort of congestion at the door, because doors are, of course, limited. So this actually helped us in brainstorming different types of policies and that can be implemented at the university level. So yeah, I think I already showed this. And if you are more interested in learning about these, please feel free to contact me, and I can share the relevant research papers. And we do have some patents also in place for all of these works. Now, to conclude with, here I actually presented two different types of modeling aspects. So one aspect was related to minimally invasive procedure, where we leverage most of the technologies from VR, AR type of systems, along with the hardware that we are always interested in. And we utilize this simulation in order to translate it to the human in the loop type of system, which can be helpful in providing the personalized training as well as support the intraoperative decision making. The second part that I presented, and I hope I presented like not too fast, but the second part was relating to the multi-resolution simulation-based decision support system, where we modeled a system which was, of course, the university policies under any kind of pandemic situation. And this system is applicable, this kind of method may be applicable to other type of applications as well, where on the higher level we try to capture the dynamics at a campus level, incorporating the single level of detail, for example GIS information, the class schedule, and all the stakeholders and all the objects that are associated with that whole system. The second aspect was the lower level model, where we basically need more detailed level of simulation uh, in order to basically understand how we can uh, how we can collect some of the parameters that might be useful at the classroom level, at the lower level, as well as they can serve some purpose into the higher level model as well. Because if we try to run everything at one level, for example, higher level, then it might get too overwhelming and it would require a lot of computation. Because with simulation, we have to run multiple replications. With this, it requires a lot of computational power as well. So in order to perform a mix and match and actually aggregate some of the information that might be used from the lower level kind of information, that actually eases out the implementation. So for example, even in order to conduct this one simulation experiment for predicting next 2 weeks of the disease transmission and the campus dynamics, it took like around like 48 hours kind of continuous run onto our server. So it is pretty heavy in terms of the computation power it requires, but it comes with a lot of power in terms of how much detail you can incorporate into the system, as well as you can get some nice dashboard that can provide you. And all of this dashboard is actually available on the cloud as well, analogic cloud, which was widely used at that time by the university uh, stakeholders. So to conclude, like my some of my ongoing works that I'm trying to conduct here at IIT Bombay with some of my students is I'm developing a decision support tool for intraoperative ultrasound for neurosurgery. So this is one of the project that we are undertaking in collaboration with neurosurgeon at Tata Memorial, Mumbai. And this has been quite a good use case in terms of modeling. The second aspect that I'm trying to translate and think from a lens of the work that I presented today was uh, on multi-resolution decision support system for logistics, and I'm also working on different hardware in the loop type of projects where we have we are trying to do some surveillance by the combination of drones, UAVs, UGVs, and how we can coordinate all of the decisions between different aspects of it. And definitely I would welcome any collaboration or any kind of further communication in terms of taking these things further. So thank you for providing me with the opportunity to present here. Uh, and I would also like to acknowledge my collaborators back in US for like collaborating to perform all of these works, and the funding agencies that actually provided us with the funding support to carry out this work. So thank you for your attention, and yeah, I'm happy to take any questions if you have.
Thank you, Dr. Jain, for accepting our request and delivering an interesting talk.
Thank
I
you.
request the audience to ask your questions, if any.
Hello, can I
Yeah,
ask a question? This is Joy Kuri here.
yeah.
Okay, so I was wondering about one aspect. So you presented a VR-based simulation environment,
Hmm.
right? Now, I suppose there are other environments which are available also, and which do the same thing. That is trying to recreate the actual situation for even for training purposes. So
Right.
how does one compare these various environments which are available, yours as well as others that are there?
Yeah. So yeah, thank you for asking that question. So first of all, uh, our goal was to provide this full cost-effective solution for solving this whole training aspect as well as decision support aspect. So the traditional training simulators that are provided, the haptic feedback is one of the aspects that are first of all missing, right? So in terms of haptic feedback, when haptic feedback are available, the cost goes up to hundreds of thousands of dollars. Whereas our system that we propose, we use simple off-the-shelf sensors that are coming up with the some of the VR vendors, and we try to recreate the haptic feedback by incorporating the real surgical tools as well as the real anatomical structures, which actually sort of combine this whole cognitive idea uh, and the tactile feedback. Now the main important aspect is, first of all, it is basically reusable. So since we are 3D printing this whole anatomical structure, so it can be reused multiple times, because right now either they perform the surgery on cadaveric models which are not reusable for this particular application, or they are very costly. So we try to come up with something in the middle which is very cost effective, which can be reusable, and which has multiple applications on other sites also, right? For example, you can integrate any set of new tools that might be upcoming into the market in a few years. So that particular tool can be easily integrated, tested out, collect feedback from the users or the doctors who are actually going to use it, and then um, decision can be taken, kind of thing. So our goal was to really focus on cost effectiveness, reusability, and access to the even a training. And it costed around, I would say, like in $1,500, you can get a nice setup at home within. Uh,
Okay. Okay. So basically, my question was more of out of academic curiosity. So suppose that we do not have any constraints on cost
Mhm.
or usability, just for a minute.
Right.
And then we have all the resources that one can need. And
Mhm.
what I'm trying to understand is there a set of metrics which we can say that this is the best representation of actual reality that could have happened? So is there something like that? Assuming for a
So,
minute that we don't consider resource constraints.
so resource constraint, one thing. So actually, the modality, the way it translates to the training is different in aspects. So for example, if we look at, so there might be some other simulators that might be very close to the realism it provides,
Hmm.
right? So one example can be like, for example, one of the type of system where we have sort of robot in that is widely used in robotics surgery, where we have sort of a robotic arms at 2D screen. So that will also provide some sort of realism and haptic feedback, right? So definitely these solutions and this solution, of course, there, but at a lesser cost and also with a lot of flexibility in terms of that you can bring on the table. That is one aspect.
Okay.
Yeah.
All right. Thank you.
Thank you.
Do you have more questions? Or okay, I guess there are no more questions. I would like to end the meeting. Thanks again, Dr. Jain. Thanks everyone for
Thank you.
attending. Have a great
Thank you.
evening.
Thank you.
Thank you. Bye.